part. Okay, hi guys. I know I don't look like Professor Raj because I'm not, but I just wanted to present about Lean on Me, which is a mental health club here at CMU, very briefly before we start lecture. So who here has heard about Lean on Me? Yay! Okay, so a couple people. So for those who don't know what Lean on Me is, we're a mental health club here at CMU, and we offer a totally free and anonymous non-crisis peer-to-peer hotline. So what that means is that if you're ever feeling stressed out or overwhelmed about life, school, or like really anything in general, you can text into this hotline and a fellow CMU student will respond, and it's totally anonymous. So all we know is that a fellow CMU student is texting in, and all you know is that a fellow CMU student is texting back. And these CMU students that are texting you back are trained to handle various mental health situations. So for example, they're trained to handle, like, for example, if you're facing like academic stress or you feel like you don't belong here, which is called imposter syndrome, because all of you guys do belong here. You got into CMU for a reason. So this is a really great resource to use. This is the only time in this class that we'll ask you to pull your phone out to put this number in. It's a really great resource. If you're ever feeling stressed out about anything at all, we're here to help. It's one thing to have like a therapist who is definitely trained to handle different situations, but can't necessarily put themselves in your shoes because they're not students. And it's another thing to have a student who can really empathize with you and put themselves in your shoes and really say, like, I understand how you're feeling. I've been through something similar. So a lot of people have said that this has been a really helpful resource, and I definitely recommend that you guys use it if you're ever feeling stressed out at all. Are there any questions?
So again, I can't emphasize this enough. This is a great resource, and the nice thing is, a great many of you will feel some reluctance going up to a professor or your advisor when you're under stress, because somehow your bosses. These are peers, so it's like going to your own peer group, and it's anonymous. So the interaction is entirely different. I cannot recommend it enough. I strongly suggest that if you're under any stress, if you don't know how to manage your time, if you're feeling overwhelmed, life is coming at you too fast, you hate your professor, whatever, call them.
Are there any questions? No? Okay, so I'll hand it over to Professor Raj. Yeah, sure, we'll do. So just a second. Okay, should I put this on you?
Yeah, yes.
Here. Okay.
Thank you.
I think we're good to go.
Wait for questions.
Yeah.
No, if there are no actual questions regarding this service, you said that like we're only allowed to take out our phones with this number, but you seem to have forgotten about the in-class polls.
Oh, that's true.
The in-class polls.
I assumed you guys would take out your laptops for that.
All right, guys, let's begin, right? Can everybody hear me? Yeah. Okay, fine. And you all have your numbers. Let's start off with a number. Who is 31? I have no question for you. Right. So we're going to be talking about representations. The story so far, we've seen that neural networks are universal approximators. You give me a function, I can compose a neural network for it. So MLPs can scan static inputs for patterns. Convolutional networks can scan inputs for patterns. Time series recurrent neural networks can analyze time series for patterns. In every case, we are speaking of the capacity of these models to perform certain tasks. But if you really want them to model a function of choice, you have to train them to do so. And when you're training them, what do they learn internally? All we've seen so far is how to train really complex models. We actually haven't discussed what happens inside the models. We're in the process of learning to model these functions. So that's what we're going to look at today. Now, here's the problem of learning as we saw it. You're given some function, maybe like that bivariate grid that you've got over here. And you must compose a model that can compute this function. Except you aren't really given the function itself. you're given training instances which consist of input-output pairs shown by these red lines here, and you have to learn the function from these pairs. Now, so in reality, what you're really going to get is something of this kind. You're going to get a bunch of samples like these red and blue dots, and you have to learn a function. For instance, if you're performing classification, you would have to learn a function that can learn to distinguish between red and blue based on the position. So it would not be given those boundaries. Based only on the dots, it has to learn this double pentagon boundary. But if it learns it properly, here's the kind of function that you would actually end up learning. The function would output a 1 inside the double pentagon and 0 outside. Except in reality, you're not going to get data of this kind. You will not get nice, cleanly separated data. You'll find that the boundaries are fuzzy. There's no point where you can clearly draw a line or any kind of curve and say everything to this side is red and everything to the other side is blue. And this is the kind of data that you're actually trying to learn your model from. So what do we end up learning? To understand this, let's go back and look at the simplest example that we can think of, a linear classifier. And specifically, I'm going to be looking at a two-dimensional example. This red dots and blue dots represent two different classes over here. Think of the red dots as representing the class 1, the blue dots as representing the class 0. And our job is to try to learn a linear hyperplane that separates the red dots from the blue dots. Now 14, who's 14? So in this particular instance, can you find me a hyperplane that actually separates the red dots from the blue dots? No. Why not? Can I perhaps wiggle it around and find a position somewhere so that the red dots are cleanly separated from the blue dots? So the right plot is just showing you the three-dimensional version of what's to the left, right? So is there any, when I'm looking for a linear classifier, I'm trying to find a hyperplane so that everything on one side of the hyperplane is red and everything on the other side is blue. And clearly, in this case, such a hyperplane doesn't exist. It doesn't matter how you position the hyperplane. They're going to have some red dots on what is nominally the blue side and some blue dots which is on what is nominally the red side. So here's a one-dimensional example. Here the inputs are one-dimensional, and as you can see, you have two classes, red and blue. The blue classes are dominant to the left, so the left side of the screen is obviously owned by the blue. The right side is owned by the by the red. Now in this case, who's 32? What would a linear classifier be for the one-dimensional example? Pardon me? It would be a threshold, right? A linear classifier for one-dimensional data is a threshold. Everything that is to the right is going to be assigned the value red. Everything to the left is assigned the value blue. So 7. You get the easy questions. Is there a threshold over here that cleanly separates the red and the blue? No. No, right? So now that's because I'm looking for a linear classifier. 21. What if I were not looking for a linear classifier? Can I train a neural network that separates the red and the blue in this case? How so? Pardon me? A sigmoid, will a sigmoid separate the red and blue over here? No, okay. So yeah, well, that's not your turn. What's your number? 23, okay, you're out. Thank you, right? There, I can do this, right? This is a universal approximator. The neural network can learn anything, so I should be able to train a function of this kind. Or 24, is that really true? Can I really train a classifier of this kind Given that the network can overfit, is it going to be possible for me to always find a classifier that cleanly separates the red and the blue, even on the training data?
No.
Why not?
Because in some cases maybe they're just not acceptable.
What would that case be?
For example, some cases that are labeled in just have two different labels.
Thank you, right? So what if I have data of this kind? I have red and blue instances which are exactly the same x value. Then I really cannot find a separator. So now I imagine over here that I have a whole bunch of points which have the same x value, but some of them are labeled red, class 1, some of them are labeled class 0. Now, again, hypothetically, let's say 90% of the data instances over here are red and 10% are blue. So in this case, what should the output be? Should it be 1 because 90% of the data instances are red, or should it be 0.9 because 90% of the data instances are red? How many of you think that 1 would be a reasonable answer here? And how many of you think 0.9 is a better answer? Okay, I agree with you. Why is 0.9 a better answer? Okay, what's your number?
45.
45, you're gone, okay. So why is 0.9 a better answer?
Because you want to have the probability.
It is actually, 0.9 is actually more informative. You can derive the fact that it's majority 1 still, but no, not your turn. I'll call your number.
Question.
Yes. Go ahead.
But okay, so I guess the thing is how does yes, I agree that the probability is a better value, but also what if it doesn't depend on the type of neurons and things you're using? If you use a
We're speaking really of the hypothetical example over here, right? We'll get to that, right? So the point is, this number here is an a posteriori probability. What do I mean by an a posteriori probability? It says of all the instances that had this x value, what fraction of them can I expect to have the label 1? And so based on the training data that I've seen, 90% of my instances are the label 1. So I'm going to think that for this particular x value, 0.9 is a good estimate of the a posteriori probability of the class 1. Now that's more informative, because you can always go back and say, okay, it's 0.9, so this is majority 1, and you can derive the fact that it's majority 1 from it, but it's more informative. But then, suppose I do this. I have a whole bunch of x's which are almost exactly the same. You're never going to get two values which are exactly the same, right? So they're all off by 10 raised to minus 17. In this case, does it suddenly become okay for you to be jiggling up and down and catching these minor variations? 26? Do you think that would be okay? Pardon me? So if I just jiggled all of my x's a little bit, so they're all almost exactly the same value, then they're not identical anymore. Does it make sense now for me to have a function which is going up and down and capturing each instance, or does it still make sense to say that in this region it's majority 1? Yeah, but then again, how do we define the majority? Because no two values are exactly the same, right? So then you would have to think of things slightly differently. The way you would have to think about it now is you still want to assign a number 0.9, but you have no idea which x to assign a 0.9 to, because no two x's are the same, right? So the way you would go about it is say, okay, let me look at this point and let me look at a small window around it. And if I look at a small window around it, and I begin counting what fraction of instances in that window have a label value 1, I'm going to get a 0.9. So then I could start off with this window at the leftmost of the picture, and I could slide it forward, and as I go left to right, I'm going to find that initially everything is labeled 0. So the fraction of instances which are labeled 0 is going to be 0. Then as I go from left to right, the red becomes more and more dominant, and so the fraction of instances which have the value 1 will keep increasing, By the time I get to the extreme right, it's going to be all 1, and in between it's going to sort of go smoothly from 0 to 1. So this is the outcome that you logically want to get. And again, there's something fuzzy over here. It depends on how wide my window is, right? Should my window be 10 raised to minus 17? Should my window be 10 raised to minus 20? Should my window be 1? Depending on how wide I make my window, the curve that I get is going to be very different. But then in general, we can sort of agree that this is the shape of output that makes sense. Now, you want your network to model the shape, right? And this shape has a meaning. The interpretation there is that it is the a posteriori probability of the class 1 given the input, who is number 18. Can you think of an activation function that has this shape? Pardon me? Perfect, right? So this is what the sigmoid looks like, which is why the sigmoid is such a beautiful activation function for your decision layer. In that you have this is for a single variable, the sigmoid is 1 over 1 plus e raised to minus w0 plus w1x. Now assume that w1 is positive. If w1 is positive, then 37. What is e raised to minus w0 plus w1x going to be when x is a very large negative number? So I'm speaking of this term here. Where was my chalk? I have 1 over 1 plus e raised to minus w0 plus w1x. What will this term be if w1 is positive and x is a large negative number? What will it be? 0. That's going to go to 0 because it's going to be e raised to minus infinity, right? So what will the sigmoid be? If this term becomes 0, what is the sigmoid going to be? It's just going to be 1, right? Okay, now who is 37? There's a 37 in the room? Who is 37? Okay. I'll call 37 later. Who's who? I called you, did I? So who's 19? 19? Yes, okay. So if x is go back and say x is w1 is positive, and if x is a very large positive number, what is this term? Wait a minute. I think we got it wrong, right? If x is a large negative number, that term is going to become infinity, so you get to become 0. If x is a large positive number, it becomes 1. So, but you can see that it sort of goes smoothly from one end to the other, right? Anyway, and your logistic perceptron is basically just a sigmoid. If you have a single input, it's just taking in the input, it's computing the logistic function, the sigmoid. And so it actually captures this kind of shape. And so what your sigmoid activation function is doing in the case of a linear, if you have just one activation function and your network consists of one sigmoid perceptron, it's computing the a posteriori probability of the class 1 given the input. Now consider a two-dimensional example. This is just a variation of the same basic idea, right? So now you'd have two-dimensional data. You're going to have some red dots, some blue dots, and what you're trying to do when you're trying to find your classifier is if you have a sigmoid activation, you're still learning a sigmoid function. The sigmoid function is still going to have the same shape, but it's going to be a sheet. And so it will be a sheet of this kind. When you're trying to find the best sigmoid for the data, you're trying to find out where to position it, how to stretch it, and how to rotate it all at once to find the best sigmoid to fit the data. But then yet again, there is no sigmoid which will cleanly separate the, so this is what the shape is going to look like, right? And there is no sigmoid, however sharp, where all the red data are going to fall on one side, all the blue data are going to fall on the other side. It's always going to give you a probability. And although the function itself is this curved sheet represents a linear classifier. Now the reason we call it a linear classifier is that if I choose any particular value, if I say if the probability assigned to class 1 is greater than 0.5, I'm going to call it class 1, then the locus of the points where the function is exactly 0.5 is going to be a straight line, a hyperplane, right? And so the boundary which separates class 1 from class 0 is still linear. So this is, although the function is curved, this is still a linear classifier. Anyway, so let's go back and see how we can estimate this model. I've given you, let's consider the one-dimensional data again, right? I've given you a bunch of data instances. Some of them are red, some of them are blue. So the red instances are all labeled 0. I just flipped my labels. The red instances are all labeled 0. The blue instances are all labeled 1. The sigmoid function itself has the form that we have on the slide. And we want to find, remember this question I asked you, how wide must the window be? We won't actually ask that question. We're going to pose the question somewhat differently. We're going to try to find the sigmoid that best fits the data. And the sigmoid is completely characterized by the W1, which tells you how steeply the sigmoid is increasing, and the W0, which tells you where it is positioned. Now, the sigmoid over here is given by they should have some lever and not have me pull this. Okay. This sigmoid gives you P of y equals 1 given x, and that's going to be 1 over 1 plus e raised to minus of w0 plus w1 x. So who is 20? Who's 20? Okay. Can you help me work out what is p equals y equals 0 given x? What is this going to be? 1 minus 1 over 1 plus e raised to minus w0 plus w1x, right? And can you simplify this? Okay, let me do this for you, right? This is simply going to be e raised to minus w0 plus w1x divided by 1 plus same term. I can divide both numerator and denominator by the numerator term. And this is simply going to become 1 over 1 plus e raised to plus w0 plus w1x. So the two are very similar. All you're changing is the sign, okay? To have a better way of defining this, characterizing this, instead of using a 0, 1 label, I'm going to use a minus 1, 1 label. So the blue class has label 1, the red class is label minus 1. If I do so, then I can generally write this, that P of y given x is 1 over 1 plus e raised to minus of y times w0 plus w1x. And you can see why this works. If y is plus 1, then this is just minus w0 plus w1x, which gives you P of y equals 1 given x. If y is minus 1, the minus and minus cancel out, so you end up with this equation over here, which is P of y equals minus 1 given x, right? And now we are given a collection of training samples, x1, y1, x2, y2. So a collection of training samples and their labels. And now, if I want to estimate the probability distribution that best explains these data, we are going to use a principle. Who's 33? Have you heard of the maximum likelihood principle? So what does it say? Perfect. So you have a parametric form for the model. And anyway, so if I look at the joint probability of all of my training samples, assuming they're all independent, it's simply the product over all of my samples of the probability of xy. And using Bayes' rule, I can just write that as product over I of p of x times p of y given x. Easy. And now if I'm modeling the probability of y given x using a sigmoid, this second term simply becomes 1 over 1 plus whatever. Yeah. The maximum likelihood rule says, and this is a statistical principle, this is a very common statistical method to learn a probability distribution, a parametric probability distribution. And the way you do it is you try to find the parameters that maximize the likelihood of the data. So we will go over this again in the next class, but the idea here is that the world is a very boring place. And because the world is boring, anything that you observe is very typical of the world. So if you're given a choice of many different distributions and say which distribution could have generated this data, you're going to pick the one for which this was the most boring set of observations to generate, which means you're going to pick the distribution which has the highest probability of generating this data. So the world is not boring, so it's not really a great principle, but that's how we work. Now, so our probability of the probability of our training data is given by this formula over here. If I take logs, which is something we often do, then the log probability of the data converts these multiplications to summations. The p of x just comes out as a summation over I log of p of x, which is the probability of the x value of the training data. And the second term here simply ends up as the summation over all training instances of the log of the probability of y given x as computed using a sigmoid. So far so good? Okay. And the maximum likelihood estimate principle says I'm going to try to learn the parameters of my model, which are the W0 and W1, which maximize this probability. Now the first term here clearly is not a function of W0 and W1. It's just the probability of the data that you sampled from the real world. So the only term that's actually a function of the model parameters is the second term. And so now we are going to try to maximize the summation over all training instances of the log of the probability of y given x for all of the training samples with respect to W0 and W1, which are the parameters of the model. Or equivalently, when I maximize the log probability, this is like the same as minimizing the negative of the log probability, correct? So this is the same as minimizing the negative log probability. And who is 38? Does this second equation look familiar? The second equation as we have it is arg min, and I'll just write these as W minus of log of P of y given x. W are the parameters. So does this look familiar? Summation over. Pardon me? That is the KL divergence, right? It is the KL divergence between the target output and the actual probability defined by the distribution. So the probability assigned to the data by the distribution, by the model. So this is identical to minimizing the KL divergence between the desired output y over here, which is what you want the output of the model to be. So ideally, when I see an instance of class 1, then I want the model to assign a probability of 1 to y equals 1 and 0 to y equals 0, and vice versa, right? That's the ideal output. And so what we are doing over here is minimizing the KL divergence between the ideal output and the probability assigned to the data by the model. Now you can't directly solve it, it needs gradient descent. But then this begins telling you something. Anytime you're actually minimizing the KL divergence between the actual output of the network, output of the logistic, and the desired output, you are performing maximum likelihood estimation of the model parameters. Okay? So going back to our problem over here, that's for a linear classifier. But most real life problems are not going to be linear. You're going to have crazy decision boundaries, far more complex than this one, number one. And number two, the boundaries themselves are going to be fuzzy, right? So let's first consider the simple problem where the classes are actually cleanly separable. So it is possible for me to draw a boundary which separates the red data from the blue data. In this case, 39. Was 39? Yes. What was the model that we used for this data? What was the model architecture in lecture 2? Yes, but what was this? What did it look like? Okay, yes. What's your number?
6.
Okay, 6 is gone. Tell me.
So you have 2 layers. The first layer categorizes each of the pentagons, and then the second layer combines them.
That's right. So this is the architecture that we had, right? We had one subnet for each of the 2 pentagons, and then a second layer which decided if either of them was 1. Now we know that it's possible for us to train a model, to construct a model that exactly separates these 2 classifiers, these two classes. And now, if I was using a threshold activation at the output, what sort of a classifier is a threshold activation function? 42. Who's 42? Yes, what sort of a classifier is it?
What is the question?
So if I'm using a threshold activation function, what sort of a classifier is a threshold? Binary, but what else? Is it linear, nonlinear? Why is it a linear classifier?
Well, it's linear with respect to the final layer because you're just picking one threshold, not other than.
So who is number 3? So why is it a linear classifier, the threshold activation?
You are using something like sigmoid activation?
So I'm not speaking of sigmoid, I'm speaking of a threshold activation. We talked about this way back in the first class, right?
Is still a linear threshold?
It's okay. So just to remind you, when you used the threshold activation, you had something like summation xi wi greater than or equal to t as your decision boundary, right? So what does the boundary itself look like? That's the equation for a hyperplane. So the boundary is summation wi xi equals t, and this is the equation for a hyperplane. So which means that the final classifier on top is actually a linear classifier. If it's a linear classifier, then for it to be separating out the red dots from the blue dots, they must be separable by a hyperplane, correct? If they are separable by a hyperplane, then what can you tell me? So here's what we have. This final classifier is a linear classifier. If it's a linear classifier, what can you tell me about the features at this point? Number 12. Who's 12? Yeah, what can you tell me about those? Pardon me?
Equation is the function of that library.
Yeah, so I want you to tell me how the outputs of the 2 neurons in the second to last layer are arranged if the output layer is a linear classifier and is doing a perfect job. Pardon me? So, okay, who is 13? Yes. Well, how will they be arranged?
I don't understand what you mean by arrangement.
So this is a classifier, linear classifier. So if it's a linear classifier doing a perfect job, what can you tell me about the classes?
Class is linearly separable.
The linearly separable. If they are linearly separable, and if the final neuron is doing a good job, then what can you tell me about the output of the 2 neurons just below it?
It's the probability of each class is
they're not computing probabilities, right? So, okay, yeah.
So the feature extractors are original in a linearly separable.
Exactly, right? So here's what you're telling me. You're struggling with this concept, but the idea is that if the final neuron is actually able to perform linear classification and separate the two classes, then it means that if you look at this y1, y2 space, in the y1, y2 space, the two classes are now linearly separable. Otherwise, the final classifier could not have separated these two classes. And so what this tells us is that this region of the network is basically this nonlinear function which converts very crazily arranged inputs and moves them around so that by the time it gets to the y1, y2 space, they're actually linearly separable. So you can think of this, and this is true not just for the ideal architecture. This has nothing to do with the nature of the architecture itself. So long as the classifier network is able, it has sufficient architecture to separate the two classes, and it learns to separate the two classes, then it means that because the final classifier is a linear classifier, it means that the rest of the network below it is basically a function, a transform which moves the data around so that by the time it comes out of this box, the two classes are linearly separable. So you can also think of this as a feature extractor which analyzes the input data and extracts linearly separable features from the input data. Now this is for a sufficient network. If the network was insufficient, so who is 15? Can you give me an example of an insufficient network for this problem? Something that cannot actually do a perfect job of classifying the double pentagon. We did this in lecture 2. Okay, you guys forget very quickly. Who's 40? Yes.
Some red dots in the pentagon are outside.
No, I'm saying that this is the data. The data are fine. I'm asking you for a network architecture which cannot classify it perfectly. Yeah. A single layer. No, if I still give you 2 layers, who's 41? Who's 41? You, yes. Okay, all right. So if I have only, okay, Vandana, you raised your hand, yes. Insufficient number of neurons. What's your number? 22 is gone. Okay. So if I had only 9 neurons in the first hidden layer, there's no way for me to draw 10 lines which will outline the 2 pentagons, correct? And so in this case, I will not be able to create a network that perfectly classifies the 2 layers. Nonetheless, if I try to train the model, what will happen is, in the ideal case, the lower classes, the portion of the network is going to move the data around until they're as linearly separable as possible. And then the final layer is going to try to separate them using a perceptron or assign probabilities for the 2 classes. It's an insufficient model for the data, but it's still going to learn separators. It's an easy poll. So 10 more seconds, guys. That's an easy poll. I'm waiting to see the first of you close. Yes. All right. So 1, 2, 3. Done. Okay. These are two easy questions. So the portion of the network until the second to last layer is essentially a feature extraction module that extracts linearly separable features from the classes. This is true. The output layer is a linear classifier that can only perform well if the rest of the network converts the data to being linearly separable, because if they're not, then a linear classifier is not going to be able to separate the data classes, right? Now, so we saw what happens if the data are actually separable and we have a sufficient network for it. But what if we have a problem of this kind? It's impossible for you to draw any kind of a boundary and say the red dots are all on one side and the green dots are all on the other side. And even if you do, it's going to be really ugly, right? So in this case, what happens? In this case, the feature extraction layer is going to transform the data such that the a posteriori probability of the classes can be modeled by logistic. So you're still going to try to move the data around, and then eventually it's going to try to move the data into something like the figure to the left, so that now you can put a sigmoid on that function, on that two-dimensional space, and so that you can actually compute the p of y given x in a reasonable manner, right? And so the feature extraction layer is going to try to move the data around until they're as linearly separable as possible. And then the final logistic is simply, the feature extraction layer is f of x. It's actually going to have computed f of x. The final logistic is computing p of y given f of x. Y is binary. But then f of x is a deterministic function of x. So y given f of x is the same as y given x, right? And it's also a one-to-one thing. So now this means that the final logistic, which is 1 plus e raised to minus w0 plus w1 times f of x, the final logistic is operating on the output of the feature extraction module. That is still computing the a posteriori probability of the class given the input. So what this means is that this entire module, this entire network, if it's trained properly, it's eventually going to be computing p of y given x. It's computing if you train the network to minimize the KL divergence between the true and the actual outputs of the network, it is going to be computing the a posteriori probability of y, the class, given the input x as best as it can. And so the actual training mechanism, if you're minimizing the KL divergence, then the parameters of both the final logistic and the rest of the network are optimized by the training mechanism to perform maximum likelihood training. So anytime you train your model to minimize the KL divergence, what you're actually doing is training a statistical model. It's not a mechanical computation that fits a function. In a classification problem, you're always training a statistical model which computes the a posteriori probability of the class given the input. And in fact, it's a maximum likelihood estimator that's learning the parameters of the network to maximize the probability of your training data. So that is yes?
Are we assuming that we have a uniform prior?
The prior disappeared. Remember this? When we were doing this, way back when, p of x is no longer a function of the parameters. The only thing the parameters actually affect are the conditional probability of y given x. So it is a maximum likelihood estimator of the model. And the model itself is only able to capture the a posteriori probability of the classes. Right? And yes, Paul too. Tell me when we have 100. Okay. All right, 5 seconds, guys. That was an easy poll. You should be able to answer it. But then 3 of 4 statements are right. The 4th statement is not something that we've actually talked about so far, in that if the lower feature extractor is actually extracting linearly separable features from the data, then you should be able to use any linear classifier once you've actually separated the data out, right, or extracted linearly separable features from the data. You're no longer required or restricted to be just using a logistic function. You could very well extract these mostly linearly separable features and then stick an SVM on it, and it should do just fine, right? Or maybe even better than your logistic. So here's the story so far. A classification MLP actually comprises 2 components: a feature extraction network that converts the inputs into linearly separable features, or nearly linearly separable features, and a final linear classifier that operates on the linearly separable features. So, and furthermore, when you use a softmax is just a generalization of the logistic function. The final layer of the network actually computes a posteriori probabilities of the classes, and training the network to minimize the KL divergence is identical to maximum likelihood training of the model, right? So far so good. We know that the entire block until the classification layer is learning linearly separable features. What about the guys underneath? We know what comes out of the penultimate layer. But what about the layers before the penultimate layer? What exactly do they do? What happens is that as the data goes through the network, the classes become increasingly linearly separable, because the model has to work on increasing the linear separability of the classes. And so here's a nice example of what happens. In this case, we are just trying to train a small network to learn a circular decision boundary. The network has only 3 hidden neurons. Each of them has a tan H activation. Now, remember how this whole thing works. When I have the input is 2-dimensional in this example. So is there an eraser here? The first thing that happens when you train your network, the input is 2-dimensional, right? Is you have a 2-dimensional input, and that is being multiplied by a three times 2 weights matrix. So this is converting the 2-dimensional input to a 3-dimensional vector. But although it's a 3-dimensional vector, who's with 34? What is the dimensionality of the space of the manifold in which the data are going to lie? 3? Well, I assume my question is not clear. But the point is, if I take a 2-dimensional space and multiply it by a 3x2 matrix, is it going to increase the dimensionality of the data? Am I adding more information? No, right? Is it going to increase the dimensionality of the data? Can everybody say no together? No. Okay, thank you, right? So what will happen is that now this is going to become a 2-dimensional plane in 3-dimensional space. And so when I'm moving this stuff, when I change my W, I'm just changing the orientation and position of this plane in this space. So over here, we've used several thousand samples for our network. When you multiply by the first weight matrix, it's just going to position the plane in a 3-dimensional space. And then you apply a tan H. A tan H is going to distort the values non-linearly, right? And so when you distort the values, that plane is now going to get distorted. And now it's no longer going to be a plane. It is still going to be a two-dimensional surface, but it will be a curved two-dimensional surface. And now, subsequently, I'm multiplying the curved three-dimensional points, which represent this curved two-dimensional surface, by a 1 cross 3 weights matrix, and projecting that thing down to a one-dimensional point. So basically, after I put this through the tan H, this may become, this function, this surface may become something like this. It's going to become a curved surface because the tan H is going to stretch and shrink the individual values. And then when I multiply that by a 1 cross 3 matrix weights vector, that weights vector is going to be some vector in this three-dimensional space. And I'm projecting all this entire surface onto this one line, right? And so this here is the projection of the line over here. That's the curved surface, and the one to the left here is the projection of the line. Let's see how the entire training goes as you sort of go through the iterations. And you can see how it sort of learns the weight matrix to position the space plane in the three-dimensional space, and then stretch it out using the tan H, and then find the second line so that when you project the warped surface onto this line, the blue and the red become separate, right? And so this is basically the entire operation over here is about increasing as you go. The first layer positions the data so that if you transform it and then project it onto the weights of the second layer, the classes have become separated. Now if you have something that's more complex like a Sapphire, here you have many classes, and these are all, we've taken two-dimensional projections. The classes are shown by the colors. We've taken two-dimensional projections, and we're showing you the two-dimensional projections for all of the classes through the various layers. The first one is the input. The first one is the input, second layer, third layer, fourth layer, fifth layer, sixth layer, seventh layer, eighth layer, right? This is an 11-layer network. And you can see how that goes. You can see that as you go through the training, the classes begin to get increasingly separable as you go through the layers. And in fact, way before you get to the final layer, the classes are already linearly separable. The last three layers over here not doing very much. They just, because the classes have been separated. That's in 2 dimensions. If I actually project it onto 3 dimensions, you can see how all of the classes are being put into regions of the space where the classes can be separated by hyperplanes. So basically what's happening is that as you go through the network, each layer increases the linear separability of the classes. That's really what is happening here, and this is because the final layer can only operate on linearly separable classes. So anyway, questions? Yeah.
So is it kind of like LDA, the linear discriminant analysis?
This is non-linear. This is not LDA, right? You're actually transforming the data.
Yeah, but the strategy and the whole process is kind of like...
It's like you can think of it as a non-linear version of LDA. Yes.
Okay, thank you.
Very nice. Okay. So we've seen what the network learns at the output. We've seen how it sort of operates on the data, increasing the separability between the classes till you get to the output. But then what more can you say about what's happening in between? What do the individual perceptrons capture? To see that, let's consider the basic perceptron itself. Now, a basic perceptron, again, I'm using a threshold activation for illustrative purposes. The perceptron looks at the weighted sum of the inputs, which is the same as taking the inner product between the weights and the inputs, and it's comparing this inner product to a threshold. Now, if I think of it in vector spaces, the weights form a vector, and suppose, who's 17? Suppose I take an inner product between 2 vectors of the same length, then what does the inner product quantify? It's a badly posed question, but you guys should be prepared for badly posed questions. Right, 43, what does it quantify? The direction, it actually quantifies the angle between the two, right? What is the inner product? It's the cosine between two vectors. So if I give you the inner product between two vectors of the same length, then you're just saying what is the cosine, asking what is the cosine between the two. Now here's something shocking I'm going to tell you. In high dimensional spaces, all data vectors are the same length. That's because as you increase the dimensionality of a space for any given upper bound, the volume of the space that lies very close to the surface of a hypersphere keeps increasing. At a high enough dimensionality, pretty much the entire volume lies on the surface or very close to the surface of a hypersphere, which means pretty much all vectors. If you take any randomly chosen vectors in high dimensional space, they're going to be the same length. So this means the inner product is basically only computing the angle between the two vectors. The neuron is going to fire if the weights vector and the input are close enough in angle, and if they are far apart, it is not going to fire. And alternately stated, we are saying that if an inner product is a correlation, we are saying that the neuron will fire if the correlation between the input and the weights vector is small enough, right? So given that, suppose I was trying to just perform a digit 2 recognizer. I don't even need to train my network. I could do this with a single perceptron, and I'm trying to build a classifier which looks at pixel values on this grid and tells me if it represents a digit 2. All I would need to do is to arrange my weights in the pattern of a 2. And then anytime I compute the perceptron, it's computing the correlation between my input and the weights pattern, which is the 2. And so if I got something like this, that correlation is too low. It won't exceed a threshold. This won't fire. If I got something like this, that's going to fire because the correlation would exceed some arbitrarily chosen threshold that I have. You can make it as tight or loose as you want it to be. So the perceptron is a correlation filter. All it's trying to do is to detect how correlated the input is to its pattern of weights. That's about all the perceptron does. It's a pattern detector. This means, suppose I had a network which was looking, you must have seen these little ancient LED watches where you get these little grids of LEDs or LCDs and they read out the numbers. So you can get any odd pattern on them, but you usually only get digits. Now suppose I were to build a network which looked at these patterns and decided if these patterns were valid digits or not, then what you would expect is that the lower layer perceptrons, the first hidden layer perceptrons, would capture portions, little patterns that distinctly represent digits or not digits, and then the rest of the network is going to make decisions on whether this is a digit or not based on the patterns that these guys found, right? So this means that every one of my lower layer neurons is detecting a pattern. In other words, every one of my lower, so for example, if I had a network, then which is looking at my grid, this neuron might fire anytime it finds this pattern. This neuron might fire anytime it finds this pattern, and so on, as I've shown over here. Now suppose I provide some input and I find out which neurons have fired. So I find that of these 3 neurons, these 2 neurons have fired and this has not. Does it help me reconstruct the input? Right? So over here, if this has fired, I know that, can somebody tell me who's number 25? So if this neuron has fired, what pattern do I expect to see in the input? It's going to be exactly this pattern. This is the pattern it's looking for, right? So I can just go back and put this out here. What is that pattern? That's just the weights of the perceptron, the neuron, correct? Similarly, if this second neuron has fired, then who is this unfortunate person, number 11? Yes, what pattern do I expect to find? The top bar, right? So basically what this tells me is that and this is basically just the weights. I'm reimposing the weights of the perceptron on the output, correct? So what this tells me is that by just putting these things back together, basically I'm going to be putting the weights of the perceptron back together multiplied by the firing of the perceptron, and that should reconstruct the input. Will it do a perfect job in this case? It won't, because this network was designed to distinguish between digits and non-digits. So you don't expect to find any patterns that don't help you classify between the two. It's going to clean up the input and only retain those portions that either represent digits or do not clearly represent something that's not a digit. But in the more general case, you can make this more explicit, right? I can explicitly say I want my network to reconstruct the input. If I say that, then I can just say I want my network to read in the inputs, capture some features from it, and then put those back together and reconstruct the input. And when you do that, then you can sort of expect that these features are not going to be specific to any particular class, but they're just going to be the most highly prominent features of the input itself, right? So this is what we call an autoencoder. The simplest autoencoder is going to be something that has maybe only one neuron in the hidden layer. It's going to have this structure. You have all the input going into this neuron. It extracts a feature and then constructs that feature at the output. Now, what will this learn? To see this, let's go back and consider this a little carefully. Let's assume that the hidden layer only has a linear activation. If the hidden layer has only got a linear activation and the objective is to reconstruct the input, then here is what I would be doing. I would be training the network to minimize the squared error between the output and the input. Now it's a linear layer, so the output of the neuron is simply going to be w times x, right? W transpose times x. And the reconstructed value is going to be the output of the linear layer times w again. So you're minimizing x minus w transpose wx. That's the squared, that's the distance, that's the error. You're minimizing the squared norm if you're minimizing the L2 error. And does anybody recognize this equation at the bottom? What is it doing? Anyone? Can everyone just say aloud that's PCA? Okay, that's just principal component analysis, right? Now, here is what happens. If on the receiving side, over here I'm computing z equals wx, and then up here I'm computing w times z. W is going to be some vector, right? So the only output that you're going to be able to construct are extensions of this basic vector. There's nothing else you can construct because of the math. So regardless of the input, eventually the output is going to be just some extension of the w vector. And you're finding this w such that this extension of the w vector has the lowest error with respect to the input. So if you had some input over here, this one is going to, so this is w, so this is w transpose, right? So this portion is going to find you the projection, the inner product on the vector, and the output is going to scale this guy. So basically what you're learning is the direction of the weights vector such that if every point was approximated as a scaling of this vector, then this error that you're making is minimized over the entire training set. That's PCA. Now that's just with one hidden value, but if I actually have multiple hidden values, then the arithmetic remains the same. The output is going to be of something of this form. It's going to be W transpose whatever the hidden value is, Z, right? And so this is going to be, because it's basically a linear combination of the weights vectors, it's going to lie on a hyperplane. So regardless of the input, the output is going to lie on a hyperplane. So what this whole entire network is doing is learning a hyperplane such that when you express everything as a point on the hyperplane, the error is the lowest. So that is your those are your principal directions. You're still performing principal component analysis. That's number one. Number two, here is the key piece, that if I have this network, it doesn't matter what the input is. This portion of the network is only able to reconstruct points on the hyperplane. So regardless of the input, the output of the encoder is going to lie on the hyperplane. Okay? Now, we'll skip the poll, we're out of time. But then here's what, I just want to introduce some terminology. This entire autoencoder has two components. The first component is where it projects things, it computes some weighted combination of the inputs. The second that is the encoder. The upper portion is where it sort of activates the weights out of the outer layer of the reconstruction module by whatever is generated at this point, and that is the decoder. And so the encoder learns some representation on this hyperplane, and the decoder is going to compose the hyperplane. Now, that's what we've seen is what happens if the hidden layer only has linear activation. What happens when the hidden layer has non-linear activation? With nonlinear activation, things get a little more interesting, because when you have nonlinear activation, as we saw, nonlinear activations can fold the space. So basically what happens is, if you've got only linear activations, then the autoencoder is going to find, so let's say I have a bunch of data points of this kind. So clearly this is not a linear set of linearly arranged set of data points. If I have linear activations, the autoencoder is going to find a linear hyperplane such that when every point is expressed as some point on this hyperplane, the total error is minimized. When I begin introducing nonlinear activations, it gives me the ability to curve this surface. And so because I curve the surface, an autoencoder with nonlinear activations can actually end up learning a curved manifold of this kind to best represent the data. So an autoencoder with nonlinear activations actually performs nonlinear PCA. And the more complex the decoder is, the more layers it's got, the more nonlinear the activations are, the more complex the surface that it can capture. And so the decoder ends up capturing these complex nonlinear surfaces that best represent the overall structure of the data. And so here are some examples. We're running out of time, but yeah, we should be done. In this case, we've got data from a spiral, two-dimensional spiral, and we've learned an autoencoder for this data. The hidden representation is just a single variable. So ideally, what is the structure of the data? The data is arranged according to a spiral, right? So ideally, the decoder portion of the data should be reconstructing the spiral, and the hidden single value that comes out, that's going to give you a position on the spiral. And so because the data are kind of arranged like so, the actual structure is a spiral, and the hidden value is going to say, the decoder should be able to reconstruct the spiral, and the hidden value is going to say the actual input is closest to this point on the spiral. And when you actually train the network, you basically find that it sort of learns the structure, but not as cleanly as you would imagine. what happens is something a little crazy. As you keep varying, once the network is trained, as you keep varying the hidden representation in that single point, and you make it go from minus infinity to plus infinity, you find that the decoder sort of reconstructs the spiral in the region where you saw training data. And once you go outside the region where you had training data, the thing can reconstruct pretty any odd thing. Or here's another one. This is where we have data on a sinusoid. And once again, you see that the decoder is actually ending up capturing the structure of the sinusoid. The point being, this performs some kind of nonlinear principal component analysis, right? Now, here's the, now, when the autoencoder actually has this hidden representation that's a lower dimensionality than the input itself, this is what we'll call a bottleneck. And that is the kind of network architecture that we really like, because the hypothesis over here is that the data are lying on a surface of a lower dimensionality than the space itself. So here, for example, the data lie on a one-dimensional curve or very close to a one-dimensional curve in two-dimensional space. That is the hypothesis, which is why the network has just one hidden representation. Now, number one hidden unit in the center. Now, the other point is that if I represent, once you've trained this network, then if I modify the value out here, and if I vary the inputs of the decoder, it cannot recreate the general input. It can only recreate something that is actually on the manifold, on the surface that the decoder can compose. And that gives us some useful properties. It says that when the network is trained properly, this decoder basically represents the surface on which data typical to that source lie. And then if you chose a random data point on the surface, which is to say, if I gave some random input to this decoder will arbitrarily generate data which kind of look like the data that was used to train the network. So to give you an example, if you trained your network on digits and then you use the decoder and just gave it some random input, you would expect the output to also look somewhat like digits. And if you don't believe me, here's an example where we trained an autoencoder on spectrograms of saxophone music. Then you throw away the encoder, and then you just feed it random inputs, the decoder with random inputs. Here's an example where just this one neuron was excited and the rest were not. And here's what it sounds like. Wait, this worked 5 minutes ago and now it doesn't. Guess what? The Zoom guys came and messed me up, right? Let's see if this works. That's a total failure. Our tech guys are amazing. I tested this first before class, but here's what you get. When you actually play this out, I don't know. Does this work? Maybe. Absolutely not. It says the microphone is off. Let's see. It never fails. It never ever fails. Okay. So here's what. Here's an encoder that's been trained only on saxophone. And if once I've trained it, I just use the decoder to generate spectrographic images. Here's what it looks like. Here's what it sounds like. Randomly excited it with some random input. The output sounds very much like a saxophone. A different input also sounds like a saxophone. This one's trained on a clarinet. It doesn't sound like a note. It sounds like something that could have been played with a clarinet with combinations of notes. So it actually ends up generating things that could have been from the source. The point being that a properly trained autoencoder learns the structure of the surface on which the data lies, and if you choose a random point on it, it is going to look like that data generated from that distribution. This is something that will come back to us in the next class. So please go and check the polls out there on the slides. But here's a very cute application that I like to end with. This is a classic example of trying to separate mixed sounds. So given mixed sound from multiple sources, we want to separate out the sources. So this is something called a dictionary-based technique, standard thing. You want to construct a dictionary that can only generate notes from the individual sounds from the individual sources. So for example, a dictionary for a guitar is a guitar. When you play a guitar, the only sounds you can play are guitar sounds. A dictionary for drums are drums. The only sounds you can generate from drums are drum sounds. And so if I gave you a mixed recording which had both guitar and drums, all you'd have to do is to figure out how to play the guitar and how to play the drums, so that together they sound like the music that you just heard, and then you can get the separated guitar and drum sounds. Sounds complex, doesn't it? Because, how do you play it? Let's pose this in mathematical terms. If I have an autoencoder which has been trained just on the guitar, and similarly, I have an autoencoder that has been trained just on the drums, then I know that the decoder of this guitar, the guitar decoder, when excited with any input, is going to produce guitar-like sounds. The drum decoder, when excited with any input, is going to produce drum-like sounds. So I literally have to ask myself, what must the input to the guitar decoder be, and what must the input to the drum decoder be, such that when I sum their outputs together, the result sounds like the music, it looks like the music that I just heard in the spectrographic domain. And this we know how to do, right? I have the sum of the two, sum of the outputs of the two, so I get the spectrogram for the sum. I have the mixed signal, I can look at the L2 divergence between the two, and I can use backprop, except I'm using backprop not to update the models. The models have already been trained. I'm using backprop to estimate the inputs to the two decoders. And once I've estimated the inputs to the two decoders, I've basically figured out how to play these two instruments. So now the outputs of the individual decoders are going to be the sounds from the separated sources. And see how that works. This is actually a mixed recording with two different instruments, and we've trained decoders for each of the two instruments, obviously, and stuck them into the separator. Let's see what it sounds like. I bet you never heard that one, right? Anyway, so the point is, it's not perfect. Obviously, nothing is perfect, but you get the idea. The point is that in this case, what we are exploiting is the fact that the lower layers of a network capture our pattern detectors. You can reconstruct the input by simply putting these patterns back together. You can explicitly train your network to reconstruct the input. Now, if you train the network for a classification task, the kind of patterns it's going to find are going to only be relevant to the particular task. But if you trained a generic network saying just reconstruct the input, it's still going to find all of the most relevant portion patterns in the input. Alternately viewed, the network learns the nonlinear surface in a high-dimensional space close to which all of the data lie. And if you train an autoencoder, the decoder portion of this network can only reconstruct points on the surface on which the data lie. So if you just excite it, if it is properly trained, then the decoder is going to generate data like something that is that resembles the source. And in fact, that can, as we saw, just be put to uses of this kind where the ability of the decoder to only the restricted ability of the decoder to generate data can be put to uses like denoising or source separation or what have you. So the story for the day is that Classification networks learn to predict the a posteriori probabilities of classes. The network until the final layer is a feature extractor that converts the input data to be almost linearly separable. The final layer is a classifier that operates on the linearly separable data. Now, regardless of whether you're performing classification or whether you're performing regression, the network actually learns is a maximum a posteriori estimator, and your training is maximum likelihood estimation. Secondly, neural networks can be used to perform a linear or nonlinear principal component analysis, autoencoders, because these pattern detectors actually learn which regions of the space the data lie in and learn to model this region of the space. And you can also use this to compose constructive dictionaries for the data, like in our example. So I'll stop right here. Thank you.